How can we identify unknown samples of aldehydes, ketones, and primary, secondary, tertiary alcohols? Well, this video is about that. I will go over the tests that we can carry out in the lab to identify these different organic compounds. If you find this video helpful, don't forget to share, like, and subscribe, and look out for new videos. In this video, we're going to look at how to distinguish aldehydes, ketones, and alcohols using experiments or little tests that we can carry out in the lab. Okay, so the first one we might use is the acidified permanganate test. You should have some familiarity with this. So what happens is we take a sample, an unknown sample, and we add some acidified permanganate. Often it's acidified potassium permanganate, so remember there's a K in front and no minus here. We add this purple solution to our sample. It will go purple, we'll shake it, and then we'll place it in a water bath of about 60 to 70 degrees Celsius, and we'll leave it there for about 5 minutes. If it goes colorless, that means that something has been oxidized, so it is a positive test for an alcohol or possibly an aldehyde, but not a tertiary alcohol. So a positive test, permanganate, acidified permanganate test, is it goes from purple to colorless. So here's an example of a reaction we might draw. Primary alcohol has been oxidized to a carboxylic acid, realizing that it did go through an intermediate on the way in this case. We could also have a secondary alcohol being oxidized on to a ketone. Okay, so if we're using this as a test, what would we expect, what results would we expect to get from the different alcohols, aldehydes, and ketones? So if we had a primary alcohol, we would expect that it goes to an aldehyde in its first step, and what we would expect that this to observe a purple to colorless reaction. If we had a secondary alcohol, again, in this case it will produce a ketone. We would also expect it to have a purple to colorless reaction. Tertiary alcohol, remember, we would not expect it to produce anything. It will not get oxidized by acidified potassium permanganate or acidified permanganate, so it would stay purple. Our aldehyde will be oxidized, remember, because it is an intermediate in the test for the primary alcohol. It will turn into a carboxylic acid and it will go from purple to colorless. And finally, ketone, it doesn't react. It can't be oxidized, so it will stay purple. So you need to remember these. You need to remember primary, secondary aldehydes will react with acidified permanganate test. Acidified dichromate. So if I wanted to carry out this acidified dichromate test, it's very similar to acidified permanganate, apart from the solution here is orange. So often it's acidified potassium dichromate, which is K2Cr2O7/H+ acidified. We add that to our sample. We take our sample, we put it in the water bath, and this will take a wee bit longer to change in the permanganate. But if we do have a positive test, it is going to go green. It goes from orange to green. Now what happens here, of course, is the OH is being oxidized to a carboxylic acid group. It goes from an OH to an aldehyde to a carboxylic acid. And if it's a secondary alcohol, it's oxidized to a ketone. So both reactions are very similar to what we have for permanganate. It's just a different reagent being used. In fact, they produce the same results for the organic molecules. So when we summarize it, we should get the same results. Acidified dichromate test, okay, it's orange. It's also an oxidation reaction. It does exactly the same. They're about the same strength. Acidified permanganates are a wee bit stronger, but they do the same things. Primary goes to an aldehyde, orange to green. Secondary goes to a ketone, orange to green. Tertiary doesn't react. The orange color stays. Aldehyde, again, will go from orange to green, and we expect that the ketone does not react. okay, it stays orange. So remember that the acidified dichromate, the acidified permanganate have the same positive reactions. They are just different color changes. So this one, what will happen is the orange color will go, the orange color will go green for a positive test. Okay, so we can also use something called Lucas reagent to further identify the difference between primary, secondary, and tertiary alcohols. Now, Lucas reagent is we take our sample, our organic sample, and what we add to it is concentrated hydrochloric acid. Lucas reagent in the pure sense is concentrated hydrochloric acid with a zinc chloride and hydrous zinc chloride added to it, but it will work with just concentrated hydrochloric acid. We add that and we shake the sample. Now, if it goes cloudy, now either immediately or if it takes 5 to 10 minutes, that is a positive test. But we have two types of positive test. We have it goes cloudy quickly. If it goes cloudy quickly, this is a positive test for a tertiary alcohol. So this is the only reagent that we have that will definitively tell us that we have a tertiary alcohol, and it's very useful because we add it and it goes cloudy straight away, and secondary and primary alcohols do not go cloudy straight away, so it's pretty obvious. Now, if we summarize this, it doesn't react with primary alcohols, so we get no change observed. With a secondary alcohol, it does react, and if we heated it over 5 to 10 minutes, we would undergo a substitution reaction. We would replace the OH with the Cl, and it would turn cloudy over that 5 to 10 minutes. However, this is the one that is important. A tertiary alcohol, when we add Lucas reagent, will go cloudy straight away, immediately. Okay, let's look at Fehling solution. Sometimes people use Benedict solution, or they say that they're adding Benedicts when they're adding Fehlings. Fehlings is the solution that was developed by chemists to identify aldehydes, but the solution Benedicts that biologists often use can be used just as easily. We take the sample, we add the Fehling solution, it's blue, then we heat it. So the water bath, again, 70 to 80 degrees Celsius. We leave it in here for 5 minutes, and positive test, it goes a brick red or an orange brick red. Positive observation, blue to orange. What happens here is the aldehyde will be oxidized to a carboxylic acid. However, what's happening here is the copper 2 plus ions are turning to copper 1 plus ions, and this solid that's produced here is orange, and copper 2 plus ions in solution are blue. So as the copper 2 plus ions are removed, the blue color disappears, and as the copper 2 oxide is produced, the orange color appears. So that produces the positive result that we note. Also, the strength of the oxidizing ability of the copper ions is quite weak, and it cannot oxidize a primary alcohol or secondary alcohol to the next stage. It's only strong enough to oxidize an aldehyde to a carboxylic acid. So it is a definitive test for an aldehyde. It will only react with aldehyde. And in fact, if you're using Benedict solution, when you use it in biology, you're trying to identify the aldehyde glucose. So glucose has an aldehyde group, and it's a positive test for glucose. So Fehling's or Benedict's reagent doesn't react with a primary alcohol, no change, stays blue. Doesn't react with a secondary alcohol, no change, stays blue. Doesn't react with tertiary alcohol, no change, stays blue. It does react with an aldehyde, and it goes to carboxylic acid, and it will go from blue to orange red, and it doesn't react with a ketone. So it is a definitive test here for an aldehyde. And remember, that's because it is a weak oxidizing agent. Okay, so the last test we're going to use to identify these three is called Tollens reagent. Now, Tollens reagent is made by taking silver nitrate, adding a wee bit of sodium hydroxide, you get a brown precipitate, and then redissolving the silver with ammonium ligands. That is, we are going to add the ammonia to surround the silver ions, and we get a complex ion that redissolves. So this is Tollens reagent. Now I've turned silver nitrate, I've added some sodium hydroxide, then some concentrated ammonia to make Tollens reagent. Often you'll just be given some Tollens reagent that someone has made up fresh for you to carry out this test. So I take the Tollens reagent, a testing sample, and I add it to my Tollens reagent like that, and then I shake it and I put it in a water bath. Love water baths. So 70 to 80 degrees Celsius, safe way to heat things, and if we have a bit of time, they're usually pretty good at providing the heat we need to make the reaction happen. What happens is we get a fine silver deposit on the inside of the glass tube, and it looks exactly like a silver mirror. So this is called the silver mirror test. Now, what happened here, this is a positive test for an aldehyde. The silver in the silver complex, the silver 1+, is reduced to silver metal at the same time as the aldehyde is oxidized to carboxylic acid. Because remember, this is an oxidation reduction reaction. So we have something getting oxidized, this is the aldehyde, and something getting reduced, that is the silver plus. And we produce the final product of the silver metal, and of course we produce the carboxylic acid as well. But we're interested in this positive test. Now, that only works, doesn't work for a primary alcohol, isn't strong enough to oxidize a primary alcohol, no change, isn't strong enough to oxidize a secondary alcohol. Of course it won't oxidize a tertiary alcohol, nothing does, but it is strong enough to oxidize an aldehyde and turn it to a carboxylic acid. We produce a silver mirror, a definitive test, my favorite one really for identifying an aldehyde. Remember, Tollens reagent is a weak oxidizing agent, just like Fehling's reagent or Benedict's solution. It's only strong enough to oxidize the aldehyde, so it makes a definitive test for aldehyde. Okay, those are the tests, but the type of questions are likely to ask us are ones like this. Like, explain how Benedict's solution can be used to distinguish between pentanal, which is an aldehyde, and pentan-threone, which is a ketone. Your answer should include observations, the type of reaction, and structural formula of any organic product. So of course, when we look at this and we see it's Benedict's, we know Benedict's is a definitive test for an aldehyde. Pentanal is an aldehyde, so we're going to have a positive reaction with that and no reaction with anything else, especially the ketone. So we add 2 ml of each sample and 1 ml of Benedict solution. We heat in a water bath. The sample that changes color, we're given the observation now, blue to orange is the aldehyde, pentanal. This is an oxidation. I've identified the type of reaction that produces butanoic acid. They want me to draw the structural formula. There it is, down the bottom. And just to be safe, I've said pentan-threone does not react with Benedict solution. I could have said because it's a ketone, but that's a good enough answer for this question. I'm thorough. I've hit all the bullet points that they've asked me to cover. Let's have a look at another type of question. So they want us to describe a series of tests, more than one test we carry out, including the observations and appropriate equations to distinguish between unlabeled samples of butanal, aldehyde, butan-1-ol, primary alcohol, and 2-methyl-propan-2-ol. Okay, that's a tertiary alcohol. So let's start and see if we can identify the aldehyde first, because we know 3 definitive tests, well 2. We know Tollens reagent, silver mirror test. We know Fehling's or Benedict solution, which is the same thing. Let's just say Benedict's here then. So we take 2 ml of each sample. Oh no, we're going to add Fehling's solution and heat it in the water bath. The sample that goes from blue to orange, remember this is a definitive test, is the aldehyde butanol. So what we can now say is we know which one is butanol. We're now going to test the other two. So the other two, remember, are the primary alcohol and the tertiary alcohol. So we can either here use Lucas reagent, it would give us a positive test for tertiary alcohol, or we could use acidified dichromate or acidified permanganate, it would give us a positive test for the primary alcohol. So what we're going to do here is we take 2 mils of the samples that we haven't identified. We're going to add acidified dichromate. So that's orange, remember, we put it in the water bath, and the sample that changes from orange to green is the primary alcohol, butan-1-ol. So now we've identified the primary alcohol. Of course, the one that hasn't reacted both times is going to be the tertiary alcohol, and that's 2-methylpropan-2-ol. Okay, I hope this video has helped you get your head around how you might identify aldehydes, ketones, and primary alcohols in the lab. Okay, if you've got to this part of the video, you've obviously watched all the examples that I had on those 3 questions. Hopefully this has fortified your understanding of geometric isomers, and you are now well prepared to go and attack that exam. Good luck, and if you found this video useful, don't forget to like it, subscribe, and look out for new videos that I might put up by clicking that bell. See you later.